Welcome back, folks. We're going to get our third and final fundamental law of circuit analysis. Once you know these three laws, you know everything you need to know to analyze any circuit. That usually gets a groan in class. I'll let you do that in the privacy of your own home. You're not going to be very good at it, but these are the foundational things that we build off of as we begin to analyze circuits. Everything comes back to these three laws. This is Kirchhoff's current law. Okay, so let's get a circuit to play with. We know how to analyze this circuit using current dividers. We already did. I think it's the first one that we applied the current divider to, and we found the currents accordingly. And I just have them labeled up there. If you want to see how we did that with the current divider, go back and watch a few videos ago to figure that out. So this is Kirchhoff's current law. And we very frequently abbreviate that one as KCL. Okay? So you'll hear me throughout the semester say everything goes back to KVL, KCL, and Ohm's law. Those are our three fundamental laws that we're dealing with. Okay. In the case of Kirchhoff's current law, he's going to state it again. I have it typed up all nice and pretty for you. Okay. The algebraic sum of currents entering a node is 0. Okay, so this is KCL. We have this word again, algebraic, so we have to respect sign once again. Okay, so respect sign. Consider the polarity. Is the current going in or is it coming out? I think of this one as cars going into an intersection. If let's pretend we're in Hartford and the traffic's horrible and one car leaves an intersection and everybody's back, bumper to bumper. One car leaves, then another one can enter. Everything going into the intersection, something has to pop out. It doesn't matter which direction it pops out, but it has to make space for the stuff coming in. Okay, and that's what we're going to do mathematically with our currents. So the algebraic sum of currents entering a node is 0. Okay, so we have to pick a node in our circuit to work with. In this circuit, there's only 2 nodes. So we flip a coin, a virtual coin. If I had a real one, I would totally do it for you. But I'm going to end up writing them both anyways. Let's take the top node, okay, and I'll just draw a big old dot there, okay, but the node really extends all the way out here. All 3 components are connected to that top node. And I've got 3 things attached to it, so I'm going to end up with 3 terms of my KCL. So let's go ahead and start writing that. This 3 milliamps is entering that node. In my mind, since I'm entering it, I'm adding something to it. And if I'm adding something to it, then it's going to be plus. Okay, so I'm going to say plus 3 milliamps. All right. Coming over here, I'm looking at this 2 milliamps that's flowing down through the resistor, and that 2 milliamps is leaving the top node. So I've got to keep in mind which node I'm writing this for. I'm writing it for this one. The 2 milliamps is going away from it. Since it's going away from it, I'm going to call that minus 2 milliamps. All right, last one over here. This one is flowing in this direction. So once again, it's a minus, and it's minus 1 milliamp. And that's equal to 0. Those are all 3 components connected to the node. I've accounted for all currents. It's an equation, so it's got to be equal to something, and that's where that 0 comes from, right? So it's all equal to 0. 3 minus 2 minus 1 is 0. I trust that you can do that in your head without pulling out the calculator. Okay, so that's great. That's great. But what if we picked the other node? Okay, let's go back to Bizarro World, throw the dice in the air, and say, what if I pick this bottom node? Would it still work out? And it would. It's a law, just like Kirchhoff's voltage law. Kirchhoff's current law has to be followed if all of the analysis is going to work out. Our analysis here was using current dividers. We're checking it with KCL. Okay, so let's take that red node, and once again, we've got 1, 2, 3 things connected to it. I'm going to get 3 terms in my KCL equation for that node. The 3 mils is now going away from the red node. So it's going to be minus 3 milliamps, often referred to as mils. I don't think I've said that yet. So there you go. This 2 mils is flowing into the red node, so it's going to be plus. Okay, and this 1 mil over here is also flowing in, so it will also be plus. And I get 1 milliamp. Okay, those are all the components connected to the node, and it's equal to 0. Negative 3 plus 2 plus 1 ends up being 0 as well. Okay, so that's the long and the short of Kirchhoff's current law. We're going to practice it with a few examples like I tend to do. Oh, I have a good example for you. I remembered one. I promised you something in an earlier video. Maybe you've forgotten by now, but we'll go back and do that now that we have KVL and KCL. Okay, we got to remember two things when we're writing KCLs. The number of terms matches the number of components, elements connected to the node. Okay, and second, all, and I mean all, terms must be currents. They must have the unit amperes. Too often I see people trying to add volts to amps, and it just doesn't work. You can't do it. You should know better. Okay, if you don't, you do now. The example I like to use is I usually stand somebody if they make the mistake in class. You can make the mistake at home, but if they make the mistake in class, I stand them up and I say, okay, walk forward 5 feet. And they walk forward 5 feet. I say, take a left. And they turn left. And I say, okay, now walk forward 7 ohms. And you just can't add feet to ohms. And similarly, you can't add volts to amps. They're different things. Don't do it. So make sure all your terms in your KCLs are currents. Okay, on to examples. We got to practice this a little bit so that we get good at it and we can write it as we are analyzing circuits. All right, stay tuned and good luck.